and also geometric series. Then let's go to the most important uh, mathematics, that is the vector. So I think most of you have learned about the difference between what is vector, but in our GCSE did not know the term what is called a scalar. So this term are two different categories. So for vector, it has magnitude and also direction. I think you know about it already. So one of the example is the velocities, velocity, acceleration, and displacement, force, and so on. And for scalar, it only has a magnitude, but it does not have a direction. So most of the physical quantities can be categorized into these two groups, but not all. But some of the quantity, we use the term tensor for some of the quantities, but I can't tell you what tensor is. So one of the example of the tensor is a matrix. If you have learned about the matrix, then you know that the operation of matrix is quite different from the vector and the scalar. So what is a scalar? Uh, what you have learned in primary school, I think they are all scalars, just like the real numbers. Okay. It only has a magnitude but without any direction. So then let's move on. So first of all, magnitudes, I think it's easy to understand. Let's say $10. Okay, you know 10 is a magnitude, and 10 meter, 10 is a magnitude. And how about direction? You may say north, south, east, and west is a direction, but how we define the direction mathematically? So let me draw a coordinating system. Okay, coordinate system x y. Okay, so let's say there's a one point. So let's say this is the point with the coordinate 0 and 1. So uh, if that quantity contains a direction, okay, the representation of that quantity will change if the coordinate system will rotate. So let's say I rotate the coordinate system by 90 degree anti-clockwise. So this is the y-axis, okay, y pi axis, and then this is the x pi axis, okay. So that means I rotate it by 90 degree, okay, and then I get a new coordinate axis. So in the red coordinate system, okay, then the point is no longer 0, 1. The point will becomes 1, 0, is it? Because the point lies on the new x-axis. And then you can see the representation of the quantity change when the coordinate system rotates. Okay, so that's what we mean by direction. Okay, so let's say for this example, you will see that the coordinates can be you can treat the coordinate as a vector. Uh, you may know that sometimes we use plus or minus sign to represent the direction of a vector. So let's say plus 5 meter, that means it's moving forward by 5 meter. If you're talking about negative 5 meter, that means moving backwards by 5 meter. So we use plus or minus to represent the direction. But sometimes you may not understand why, let's say, you gain $5 and you lost $5. The plus and minus sign here does not represent direction. Because even though your coin's axis rotates, if you gain $5, still gain $5, is it? If you lost $5, still lost $5, okay? But for this case, if you rotate the coordinate system by 180 degree, okay? So let's say this is the x-axis, okay? After you rotate it, and then uh, this direction becomes a positive direction, and then the coordinate the sign will change. Here will become -5, here will become +5. Okay, so I hope you understand that uh, uh, whenever you see there's a plus or minus, it doesn't mean that there contains the plus or minus represent the direction. So then let's move on. To represent a vector, actually you learned it in Form 3 already. So to you can use a arrow, okay, to use the arrow to represent the vector. Because the vector contains a magnitude and also the direction. The magnitude is represented by the length of the vector, the length of the arrow. Okay, the length represents the magnitude. And then the arrow, the direction it points, the arrow points to is just the direction of the vector. So to write down the vector, let's say this point is point A, this is point B. So we can use A, B, okay, and then with a head on it to represent the vector pointing from A to B. And we can also use a small letter one small letter to represent the vector. Okay, and if you don't like the head, you can use the bolded letters. But of course, in your paper, okay, no matter it is in public exam or in commission, you never uh, write the vector like this. And in engineering textbook, they may use underline to represent the vector. Okay, so these all represent a vector pointing from A to B. Okay, I think right now it's quite easy. Then we are going to look at because the vector list is another category of the number. All the all the operations of the vector should be defined in another way, other than how you do it with the scalar. That means a real number. So bear in mind that all the operation of the vector are totally different. So first of all, we look at how two vectors will equal to each other. So if we are talking about vector A equal to vector B, so these two vectors are equal if and only if they have equal magnitude and same direction. So that means same direction. That means they are parallel to each other. Okay. So we are talking about A equal to B. It also implies that vector A is parallel to vector B. Okay. And they have the same magnitude. That means they have the same length. And then if it can form a parallelogram here. Okay. Parallelogram. There are parallel lines with equal size, so that it can form parallelogram. So that if the two vectors have the same magnitude, but they have different direction, then these two are not equal to each other. Okay, these two vectors are not equal to each other because they point to different directions. So just for example, if an object is moving at constant speed in a circle, so the direction of the motion, direction of the motion changes with time, and then we will say that the velocity is not a constant because the velocity here is not equal to the velocity here. So the velocity in this case changes. Okay, velocity is a vector. It also contains the direction. Because the direction of the velocity changes, so the velocity in the circular motion changes. Then let's move on. Then let's go to the addition of the two vectors. So most likely I will just suggest you to use the triangle rule. For triangle rule, it's just look like if you want to add these two vectors together, and I highly suggest when I'm drawing here, you also write on your piece of paper, and then while you are writing, you can understand better. Now, Then how do we do the addition of the two vectors? I think you have learned it already in Form 3 or Form in RGCSE. So you move the two vectors such that the head meets the tail. You can see at this point, okay? The head of vector A meets the tail of the vector B. And then you can consider that there's a man walking from here. This is the starting point, and this is the middle point, and then this is the final point. So then the addition of these two vectors is just a vector pointing from the starting point to the end point. So let me ask a question. Maybe you can help me to draw it on on the board here. So how can we prove that A plus B equal to B plus A by drawing? Remember that vector is a entirely new quantity to you. So everything should be defined carefully. Even though it seems like in scalar 1 plus 2 equal to 2 plus 1. But in vector, it may not be like that. Especially for later on for the multiplication. Sometimes 1 times 2 in vector, okay, is not equal to 2 times 1 in vector. So who can who would like to try to do this one? Hello, hello. Who would like to try to show that A plus B to B plus A? June, will try to draw it and then she show that A plus B to B plus A. Now when I define A plus B, I draw the vector A, I connect the head of vector A to the tail of the vector B. So that when you draw the vector B plus vector A, you should use the head of vector B connect to the uh, tail of the vector A. Okay, which you can try to draw it on the using Zoom. Whenever you try to you can you see the draw button? Yeah. Can you see the draw button? And yeah. Mm, yeah, that's it. Okay. So this is vector B. Yeah, this is vector A. Then you can see that when you're looking at the lower triangle, okay, this is the hypotenuse of this triangle is just B plus vector B plus A, and then this shows you that vector A plus B equal to vector B plus A. And remember why they can form a parallelogram here, okay? Because all the opposite sides are equal and parallel to each other. Okay. Then let's move on. Oh, I didn't draw it on okay, never mind lah. I hope. So how about if we want to add three or more vectors together? I will still suggest you to use the head to tail method. That is triangle rule. If you are using a parallelogram, it will become very complicated because you need to do the addition of two vectors first and two by two, okay? And then it will be very complicated. For triangle rule or the head to tail method, it doesn't matter how many vectors you need to do. You can do 10, 100 or more. So let's say if vector A, B, C, okay? So you're just joining the head to tail together. And then the vector that is pointing from the starting point to the end point is the addition of these three vectors, okay? That's it. Mm. Oh, okay. The next one is about the position vector and its addition. So position vector depends on the coordinate system that you're using. So just for example, just let's use a 2D coordinate first. So this here is a y-axis. This is the x-axis. So this is a point of the origin. So let's say this is a point of vector, the point A. So position vector is just a vector pointing from point O to point A. Okay. So you can label this vector as a vector OA. Is it? Let's say right here, there's another vector. There's a vector B. Sorry, this is another point. There's a vector B. So position vector is just a point pointing from the origin to that point. So this is a vector OB. If you write down the vectors in terms of the notation like AOB, OB, AOA, then sometimes it's easier for you to do the addition. So let's say for example, when I want to add the vector OA to the vector AB, so AB is a vector pointing from A to B. If you draw the diagram, I hope it's quite easy for you to understand. Vector AB plus vector O, vector OA plus vector AB equal to vector OB, is it? Using the head to tail method or the triangle rule. And then actually if you're not drawing a diagram, it's still easy for you to understand. It just look like the A and A can cancel out each other, and then what is left is OB. For let's give you another example. Let's OA plus AB plus BC. Then the A can be cancelled out, the B can be cancelled out. Only thing left is OC. Okay, this is a vector OC. So without drawing a diagram, you still can do the addition of the position vector very easily. Then let's move on. So what is the meaning of the sum of the vectors equal to zero? I'll be aware that this is the zero vector. This is not equal to the scalar zero. These two are not equal to each other. They are of different classes, different categories. Okay, so they're not equal to each other. So for let's define the zero vector first. Okay, zero vector is a vector that has the magnitude equal to zero, and the direction is undefined. It's not pointing anywhere actually for the zero vector. If we are talking about the sum of the vector equal to zero, now we cannot draw the zero vector by using an arrow. Whenever you draw an arrow, there has a length, that means there has a magnitude. But zero vector has zero magnitude. For the sum of the vector equal to zero, just for example, if I add two uh, uh, three vectors together, okay, right? If they can form a triangle, so that means all the head to tail are connected together. Then the sum of these three vectors are equal to zero vectors. Okay. Uh, let's consider like this. So this is the starting point. So A starting from A and then add to B and add to C, and then you can see the starting point and the end point are the same point. So that means uh, the magnitude is zero. That it should be a zero vector. So if it's for a four, if it is an addition of four vectors, let me draw something. Maybe it looks like quite weird. Okay, it just looks like a bit weird. Okay, but actually you can draw the sum like uh this, just the same, but the order to do the addition are different. You can still that to see the starting point equal to the end point. So that means they add up together still equal to zero. Okay. So that means whenever they have n vectors, the sum of n vectors equals zero. Then those n vectors can form a closed loop. That means the starting point will join the will meet the end point. And then if there's two vectors, okay, only the sum of two vectors equals zero, then they should be parallel to each other, but they should be opposite to each other and have equal magnitude. Okay. So in this case, a plus b equals zero. That's it. It will be quite useful later on when we are doing with the chapter of force. So negative vector, if this is a vector A, negative vector has a they're in opposite direction as vector A, okay? They're in opposite direction. But the magnitude are still the same. Let me introduce how we draw the magnitude, how do we represent the magnitude of vector A. So for vector A, if we want to represent the magnitude, we just add two uh, vertical lines. So you just it just looks like the absolute value in real numbers. I hope you have learned it already. Is it? Have you learned it? Right. You're so silent. Okay. So let me ask you one question. Have you learned the absolute value in core mathematics? Or have you learned it by yourself? Okay. Whatever. It doesn't matter. You learn it. So what does the absolute value do? So uh, if the value of x is positive, it just gives you back the x. If the value of x is negative, then you turn the value to become positive by multiplying a negative sign here. Okay, that's why you can see how uh, the above calculations. And then if for a vector, if you add it just look like the absolute sign, but you just put and it means the magnitude of the vector. So let's say let's draw a circle here. Alright, let's draw a circle here. So this is the center of the circle. The obviously you understand that vector A is not equal to vector B because the directions are not the same. And then but the magnitude of the vector A and magnitude of vector B equal to the radius of the circle. So they are equal. They have equal magnitude. Okay, this is just one example. For the negative vectors, okay, for the negative vectors, they have equal magnitude actually. Because they have the same length, but they are pointing to opposite direction. And then you can also see that the vector A plus a negative vector A equals zero because the starting point meets the end point when doing the addition. So the next one is doing the subtraction of the vector. So now by doing a subtraction, I just advise you to consider it as a addition. So vector A minus vector B, you can consider as vector A plus negative vector B. Okay. Uh, may you try to draw it by yourself? May you just try to draw it on a piece of paper and say me how you do the subtraction in this case. Remember that to do the subtraction, you first of all need to change the to consider as a vector A plus negative B. After you draw it, you send it into the WhatsApp group. Okay. Then you also do the draw the vector A minus vector B. I mean, you also draw the result of the subtraction. Okay. So what is this vector? It's not opposite to B. But we are doing A minus B, not B minus A. A minus B is just vector A plus negative B. Hmm. Oh, okay, let me draw it. So you still need to use the head to tail method, okay? Not head to head to tail method. Okay, let me draw it. Okay, let me draw it. Sorry. Okay. So you consider it's a vector A plus negative vector negative B. And then this vector A, this is vector negative B, and do the subtract you add these two together, okay? Because you are converting the subtraction question to a addition question. And then this is a starting point and end point. So this is a vector A plus negative B. That's equal to A minus B. Okay. So let me ask you another question. Let me add one slide here. So sometimes if you want to do the subtraction of two vectors, we'll put the vector A and vector B's tail together. This B This is A, B, okay? Because we can form a triangle. Okay? But let me ask you, okay? This is the first one, the first vector, okay? This is the second vector. So is the which one is the vector A minus B? If you say yes, that's the first one. If you say no, that's the second one. Or just one has not done it. How about the answer is the first one. So negative B is this vector, is it? And you do the addition of A and negative B. So this is starting point, this is end point. So the answer is the first one. Am I drawing? Okay, I'm drawing on it. So the answer is the first one. Let me erase the others. Okay. So then let's move on. Okay. We still have a lot to cover today. So unit vector. Unit vector 咧，sometimes so let's say for speed, okay, you know speed is defined as distance over time. So in wording, instead of using the formula, you can also define it as a distance per unit time. You may see this word, okay, per unit, okay, per unit. You may also, let's say, for how to define the specific heat capacity. So you would say this is a heat transfer uh, per unit mass per unit temperature. So the unit here, it means one. So when you're talking about the unit vector, it means that is a vector with the magnitude one, with the magnitude equal to one. So let's say a vector A is not a unit vector. So how can I make it to become a unit vector? Although we have not learned about the uh, subtraction yet, but let me do like that. This. So actually, when you divide by the magnitude of A, so let's say the A has a magnitude 10, you divide by 10, then you get the magnitude 1. The idea is like that. To represent a unit vector, we are using another different kind of head. We are using this head for it. So you pronounce it as A head, okay? A head equal to vector A over its magnitude. That's it. The most common unit vector that we are going to use is the unit vector in the Cartesian coordinate. Cartesian coordinate is just the coordinate that is x, y, z axis. Okay. Then let me draw it. So let's consider a two-dimensional coordinate system first. So unit vector has the magnitude equal to 1. So let's say there's 0, 1, 2, 3, 4. So we define some unit vector So let's say the unit vector in the x coordinate, okay? So this is a unit vector. It it is parallel to the x-axis. It points to the positive x direction. It has a magnitude 1, and this one we define it as I, vector I. The unit vector that is parallel to the y-axis, we define it as J. Okay. You can see a dot in the I, and J is absorbed by the vector sign. So, and then this is along the x-axis, this is along the y-axis. And then I think it's not difficult to guess. For the unit vector along the c-axis, it's called ij and k. Okay. Then let me see what's in it. Okay. So why I need to introduce this one? Because after introducing the unit vectors in the Cartesian coordinates, then we can represent the vectors in Cartesian coordinates using the I and j. So still using the two-dimensional coordinates. So let's say here is a point with the coordinate that is 4, 3. So what does this 4, 3 means? Like, okay, 1, 2, 3, 4. Is it 1, 2, 3? It's not in scale, of course. And then if you're talking, let's say this is a point O, this is point A, then the vector OA, the vector OA is a vector pointing from the origin to this point. Then it can be vector OA can be considered as this vector plus this vector. Is it? And then the one at the bottom along the x-axis, the magnitude is 4. And how can we represent it? You just consider as I. That is 4I. And then similarly for the vertical here. So this is 1, 2, 3. So this is considered as JJJ. So that means it's 3J. So then the vector of OA can be considered as 4I plus 3J. That's it. Okay. And then obviously, okay, this vector OA has a magnitude 5. You know about it by using the Pythagoras theorem. So that means you can write it as like magnitude 4I plus 3J equal to 5. Okay. Then let's move on. After we represented what is the c-axis? So this is three-dimensional. So I can't draw a three-dimensional object on a 2D plane, but you try to understand it by looking it as a 3D object. So the XY c-axis are mutually perpendicular to each other. Can you think about it? We are living in a 3D space. Yeah. So then let's move on. So after you represent the vector in terms of the ij k notations, and it's very easy for you to do the addition and the subtraction. So let's say you are adding these two vectors together, aij and a2j, aij plus a2j plus or minus b1i plus b2j. Then after you do the addition and subtraction, so it becomes like this one. It just looks like that you are cheating the I and J are unknowns, x and y. Let's say 3x plus 3j, 3y plus x plus 2y. And then you're doing the addition and a subtraction like this. Okay, I think it's easy. Then let's move on. For scalar multiplication, so this is the first multiplication that we're going to learn. But actually, there are three different types of multiplication in vectors, or two. It it depends on how you define it. And we are going to learn two. Sorry, there may be four different vectors multiplication, but we are going just to learn two of it. The first one is a scalar multiplication. As stated by the name, scalar multiplication is just multiply a vector by a scalar. Okay, just like Ka. So if this is a vector A, what does it mean by 2A? If 2A, it means that the vector has been elongated two times. Okay, so the length of 2A is double of the length of vector A. And if it is 1/2A, the length is halved. And then, but if it's negative, okay, let's say negative 2A, you know, the direction is opposite, but the length has been doubled. So that is a scalar multiplication of vector A. So be aware that if vector A and vector B are parallel to each other, actually there is if and only if. Then vector A can be written as some constant times vector B. Okay, whenever these two vectors are parallel to each other, so you can express one vector as a scalar multiplication of another vector by some scalar, some constant. So then we are going to apply what we have learned so far to prove the midpoint theorem. So can anyone tell me, do you still remember what it means by the midpoint theorem? A k can be positive or negative. If k is 0, then it gives you 0. So that means 0a is 0 vector, okay? But if k is negative, the direction will be opposite. Does any one of you remember what is meant by the midpoint theorem? I think you've learned it in uniform mathematics. Yeah. Mm. Do you still remember how you prove it in uniform? Anyone? Any one of you remember it? None of you remember how you prove it?
I remember.
Hmm? Yeah?
We learned it in Form 3.
Oh, then how do you prove this theorem?
Like, if AM is equal to MB and AN is equal to NC, then MN is half of BC and MN is parallel to BC.
Then how do you prove it? You just learn this theorem, but not the proof.
Yeah, we didn't, like, learn.
Similar triangles.
Yeah, you can prove it using a similar triangle. But you are using two sides proportional and one in angle in kind. Yeah, something like that. Then you're using the similar triangle, and then you're saying the angle are equal to each other, so they're parallel to each other, and the side are parallel. Okay. Uh, yeah, that's so. But then it will be very complicated for you to prove it using the similar triangle. But let's do it using the vector. Okay. So I'm not stating the midpoint theorem in details. Okay. So what we are going to prove is mm is the midpoint. Okay. And we are going to prove that BC equal to 2nm, and also BC is parallel to nm. So by using vector, actually we have simplified the case for into one simple formula. So because if you express it in terms of the vector, so let's say vector BC equal to vector MN, it always tells you that the length of BC is double the length of NM. And also, you can see that this is a scalar multiplication. So that means these two vectors are parallel to each other. So then we are going to prove it using vector very simply, just three or four lines. So I'm starting from the left hand side. So I want to prove this one. So I'm starting from left hand side, that is BC. So I can express the vector BC as vector BA plus vector AC, is it? Just look like the A can be cancelled out. And then vector BA can be written as 2 vector MA. And vector AC can be written as 2 vector AN. Okay. Done. Is it that simple? So that means actually sometimes if you want to show that two lines are parallel to each other, vectors may be a very useful tool. It can simplify your work. You can see compare the proof using the vector to the proof using the simple triangle. Okay, we have done the proof. Then let's move on. So may we take a 5 minute break first, and then we go through the remaining session. So let's see you at 11 a.m. Okay, you can stay here. Okay, but I'll mute myself. So let's have a 5 minutes break. The first type is not that difficult. That's a scalar multiplication. But the second type will be a bit complicated. And then the second type we call it the scalar product of the vector. So you can see the name is called a scalar product. That means that there's also a type of multiplication that is called a vector product. So for scalar product, we also have another name for it. We also can call it the dot product. Dot product. Dot. The dot product. So because we are using a dot to represent the product, represent this product, and then for another product, so there's another type is called a vector product, or you can call it the cross product. We are using the cross to represent it. Okay, but in scalar, I think in scalar, 1.2 is actually equal to 1 cross 2. It doesn't matter. So there's just different symbol, but it means the same thing. But in vector, they are different. They are totally different. Okay. So for scalar product, it gives you the scalar. So that means A dot B will give you a scalar. And then the magnitude of this scalar is. So let me draw the vector A and B first. So if you this is the inclined angle between these two vectors. So vector A dot B has a magnitude magnitude A times magnitude B times cosine theta. Okay. That is how we define the A dot B. So let me give you one question. So then how we can prove that A dot B equal to B dot A? So let you think about it for 1 minute. Or do you have any question about this product? How we define this product? Do you know? Yeah. I think you try to draw it on the diagram, yeah. But actually, you can also do it like this, okay? Very simple. So because this is a value, this is a magnitude of the vector A. This is a scalar. This is a scalar. Cosine angle is also a scalar. So for scalar, let's say 1 times 2 times 3, it doesn't matter the order of the order. The order doesn't matter. So that it can do it like 2 times 1 times 3. So I can just rearrange the order here. Then this one equal to B dot A. Is it? Yeah, done. Okay, we prove it. But for cross product, A cross B does not equal to B cross A. This if you learn it, you know why it is, okay? So I also would like to talk about the geometric meaning of the scalar product. So let's draw a vector A here, vector B here. The geometric meaning is look like this one. So you consider this is a rod. This is a rod, and then there's sun here. Okay, so the rod will forms a shadow on the ground. This is a shadow, and that shadow has the length that is a cosine theta. Is it a cosine theta? And then uh, you using the length of the shadow a cosine theta times the magnitude of b vector b. Then that is how we define the scalar product. So in this case, actually, it means that no matter what is the vertical length for the vector A, these vector A will still these three different vector A's will still give you the same result of the A dot B because the shadow has they have the same length in the shadow. So A cosine theta, the magnitude of A times cosine theta is still the same. Okay, so this is one of the uh, this is a geometric meaning behind. So let's talk about some of the physics formula that you will see. We are using the uh, scalar products. Actually, whenever you see in the formula there is a cosine theta, most likely it is a scalar product. So let's say there's a work done equal to F dot S. You're going to learn it later on. The power is F dot V and so on. We're going to learn these later on. So then let's move on. So then we are going to prove the cosine law. Has any one of you learned the cosine law before? Anyone? None? None? Really? Oh, so sad. Okay. So cosine law. Let me draw a triangle first. So this is a arbitrary triangle. Okay. It doesn't matter whether it is a right angle triangle or not. So this is the sine A, B, and C. This is the inclined angle theta. Okay. So if theta A squared plus B squared plus 2AB cosine theta equal to C squared, right? So sorry. Let me think about it. So here is a minus sign.
Isn't it minus?
Yeah, here is a minus sign. Okay. So this is the cosine law. So it gives you It's useful if let's say if you know about this sine, and this angle, then you can find the opposite side of this angle, another side. Or you have the two, if you have the three sides, and you can find any angles in this triangle. Okay, no matter whether it's a right angle triangle or not. Of course, if this is a right angle triangle, you don't need to use this law. You can just simply use Pythagoras theorem and also a sine cosine tangent to find all the things you want. So then, if you want to prove this one, you still can use the Pythagoras theorem and some identity in trigonometric function, but it will be quite complicated. So we are going to use the dot product to prove it. So let's say still draw a triangle, but using the vector. So this is vector A, this is vector B. I hope you still remember. We just have done it maybe around 1 hour before. So let's say this vector. Okay, this one. So this vector is actually A minus B, is it? I hope you still remember. Okay, so this angle we call it the angle theta. Now the theta is the inclined angle between two vectors. So the angle theta here is defined as in the range of 0 degree to 180 degree. Okay, that's it. Then how can we prove it? So we are doing some very dumb thing. Okay, sorry. And this vector we also call the vector C. Okay, because this is you can consider this is triangle with the sine A, B, and C and angle theta. Okay, so you can also call this vector as vector C. And then let's do it. So we are doing some dumb thing. So you know vector C will vector A minus B. So we do a dot product. So C dot C, okay, of is equal to A minus B dot A minus B. Is it? Because C equal to A minus B. And then we're going to expand this brackets. Expand it. So you get A dot A minus B dot A, multiple it like this, and then like this. And then minus A dot B plus B dot A, B dot B. Okay. I would like to stop pause a while first. Okay, I want to show another formula first. So if you're talking about A dot A, that means a vector dot itself. And then by the definition, so it's a magnitude of vector A times the magnitude of vector A times the cosine angle. So if it is itself, the angle in between these two vectors are 0 degree. I hope you know about that. The cosine 0 degree equal to 1. So that is the magnitude of vector A squared. Okay. And in this triangle, A minus B whole square. In vectors, in vectors, you can't write like this actually. And this one is undefined actually. This one is undefined. And this one you may no one's know that what kind of multiplication that you want to do. No one's know that you want to do the dot product or the cross product. So you still need to have a dot here. Is it what you mean? So we can't write as A minus B total square. Okay. Then I would like to simplify the equation a little bit. So C dot C is C dot itself. It can be written as the magnitude of C square. So magnitude of C vector C is just C. Okay. Now we have proved that A dot B equal to B dot A. So we can combine these two together. So this is final. This is how we prove the cosine law. Okay, we have proved it already using vector. Very simple, is it? So any question right now? I'm not sure what is remaining 3 slides. Are you right here? Yeah, you draw here. Oh, you can't do it, okay? Because when you draw a square here, we don't know whether you are going to do the dot product or the scale product, or the the scale product or the vector product, because there are different types of multiplication in vectors. So normally we don't put the square there. Okay, so this is cosine law. The next one is the angle in semicircle. Angle in semicircle. So I'm not sure if you learned it or before or not. June have has you learned it? June? No? Okay, so I hope that means I think none of you have learned it before. Okay. So this is a semicircle, okay? This is a semicircle. O is the center of the semicircle. So C is any point. C is uh C is some arbitrary point on the arc AB. It's not equal to A or B. Arc AB, okay? And AB is the diameter of the circle. Then the angle ACB is 90 degrees. I think I missed one point in the dot product. So let me go back to here. And let me clear something on the board. Yeah, I missed something okay here. So for cosine theta, I hope, I'm not sure if you know about it. If the angle is in between 0 degree to 90 degree, cosine theta is always positive. If it is 90 degree, it is 0. If it's greater than 90 degree, but less than 180 degree, it's negative. So that means if you're doing the dot product, A dot B, it's positive if the angle is in this range. It's 0 if it's 90 degree. It's negative if the angle is in this range. So one very important result here is that if vector A and vector B are perpendicular to each other, then A dot B will become 0. Okay. Because cosine 90 degrees equals 0. So right here, I want to prove that this angle is 90 degrees. Of course, we are going to prove it using vectors. And that means we are going to do some dot product. So in this case, I need to define some vector by myself first. So I define this vector to be A, and this vector pointing from the center to C, we call it to be B. Okay. This is also the vector A, because OA and OB are the radius of this circle. Then if you want to show that the angle ACB is 90 degrees, then what we are going to do is to do the dot product of AC dot BC or CB. It doesn't matter, is it? Maybe AC dot BC. It doesn't matter. So can you try to express vector AC and BC in terms of the vector A and vector B, these two vectors? I'll give you just 1 minute to do it. If you like, you can type your answer in the chat. Done it? So vector AC pointing from A to C is the small a plus b, is it? Vector BC pointing from B to C, it should be B minus A. Okay? And then you expand this dot product, and then you get A dot B plus B dot B minus A dot A minus B dot A. Is it? Then next is these two can be these two are equal to each other. A dot B to B dot A. We have proved it. And then what is left is B dot B minus A dot A. So B dot B, you know, is B magnitude of B squared minus the magnitude of A squared. And then you have a look at the diagram. You know the vector A and vector B have the length that's equal to the radius of the circle. So radius squared minus radius squared, that's equal to 0. That's it. Okay? You show that AC dot BC equal to 0. Then that means AC is perpendicular to BC. Then you have shown that this angle is 90 degrees. Okay? Uh, but it may not convince you using the vector because it just looks like some mathematics. If using a geometry, you still can prove it using the geometry you have learned so far, I think. I'm not sure. So, but I'll just try to show you by using geometry. So this is center of the circle, okay? So you know these three sides have the equal length. And then I can draw some uh, con these two angles are identical to each other. So these two angles are identical to each other, is it? Okay, and then we are going to show that these two angles add up together is 90 degrees. I think it's not difficult at all right now. So let's say this is theta, this is phi. This is theta and this is phi also. And then you're just using the angle sum of triangle, of the big triangle, is it? The large triangle. So that is theta plus phi plus theta plus phi equal to 180 degrees. And it's not difficult for you to show that theta plus phi equal to 90 degrees, is it? Then this is right angle. Okay? In some of the question, you need to use this theorem to prove something. Okay. The next one is a scalar multiplication and a scalar product in Cartesian coordinate. That's all. The scalar multiplication in Cartesian coordinate is pretty simple. So what it is like let's say 2 and then 3i minus 2j, then it's just 6i minus 4j. Okay, that's it. I think it's easy. Okay, done. But for the scalar product, so let's consider a two-dimensional case first. So let's finish these thing first. Okay, I dot j, and j dot j. So I dot I, you still remember? I hope you still remember. This is a unit vector. So by the definition of the dot product or the scalar product, it's magnitude of I times magnitude of I times the cosine angle. So that's the same vectors. So the angle should be 0 degree. It's just 1 times 1 times 1, give you 1. If it's I dot j, it's just 1 times 1 times cosine 90 degree, then give you 0. Because these two vectors are perpendicular to each other. If it's j dot j, 1 times 1 times cosine 0 degree, give you 1. So let's do this multiplication. Okay. Now, so sorry. I'm writing it on using. Okay. So if you're doing the 3i dot 4i, okay, I dot I you 1, so give you 12. It's with 3i dot 5j, I dot j is 0, give you 0. So you don't need to care about it. And then negative 2j dot 5j, j dot j is 1, it gives you negative 10. And then if negative 2j dot 4i, j dot I is also 0. You don't need to care, it's 2. So make it simpler, okay? With AI, A1i plus A2j dot B1i plus B2j, and the answer will becomes, you just need to do the multiplication of the term, the x1, that is A1 plus, times B1, and then plus A2 times B2. That's it, okay? That's how we do the scale product in Cartesian coordinates. So I'll leave this one next time. So actually, I've learned a lot today. Actually, yeah. So everything is very condensed. I'll give you the assignment in the afternoon. Okay, I'll make the assignment for you to master this topic in the afternoon. We are using these topics about the we are using this kind of mathematics throughout the whole course because we are dealing with many physical quantity that are vectors. Okay. Do you have any question about today's lesson?